so from today, we will learn about the function call. Okay, so let's look at the function call in C code. Here there are two functions. One is function f, and another one is main function. Okay, so let's look at what is happening for this function call. So in C code, it's very simple. So let's look at the function f. Okay, so for this function f, we are providing the two value, which is called argument. Function arguments. Okay, so before we are calling function f, we have to provide two argument, function argument, and then the function is calling. So this statement is calling function f, right? If the function f is called, then what's happening? We have to go to the main code of the function, right? So we have to go to the implementation of the function f. Okay, so here what instruction is involved for this function call? We need to jump, right? We need to jump that the implementation of the function. Okay, then this function f is receiving the argument and then do the sum operation, and then it is doing the return, right? So when this return is reached, then this is jumping to the next place for this jump, right? So when we are calling the function, what we have to do is first we have to store function argument. Right, and then jump to function f, and then inside the function. So this example, this function is very small, but if this function is including the large local variable, like, so for instance, inside of that there is some local variable stv, which is 1000, right? So blah 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 and return. So in this case, what we have to do is that we have to prepare the local variable space, right? So we have to prepare some memory space for that function. So we are preparing memory space for function f. Okay. After that, we are executing function f. When f is executed, then final result should be stored in the returned value. So final value is stored in the returned value. So we have to store the return value to some place. Maybe we can store that result in the memory, or we can store the result in the register. We are storing the register. And finally, we are jumping back. Jump back to the caller's location. When you're translating the code, we have to follow this kind of procedure. Okay, so these steps are summarized in the next slide. Here, procedure calling, we have to handle in the parameters, function argument, the register, and transfer control to the procedure means is jumping to the function. Jump to function. And third, acquire storage for procedure means we are preparing the local variable for the function. Memory space. And then execution. And 5, place result in the register for caller. So we have to store the result value in the register. And finally, return to the place of call. So we are jump back. Okay. So the function case, the difference is that difference from the traditional jump is that when function is called, then we have to know about where is the returned address, where we have to go back, right? So that's the difference. So we learn about the branch equal and branch not equal and jump instruction. So jump instruction case is jumping to some place, but we don't know. We don't need to go back to the original location, right? So jump instruction is not enough to implement the function call, right? So we need some different instruction to implement this function. So we will learn about the jump and link instruction. Okay. So we are learn about the jump and link. Jump and link instruction. So jump and link instruction is very similar to the jump instruction, but it has additional thing. So and link. So what does it mean is jump means we are changing the program counter value, right? So program counter is changing to the address of the function. And then what we have to do is that we have to store the location that we have to come back. So the next address, so we are changing the PC value. We have to store PC plus 4, which is next instruction for the jump and link instruction. So that should be stored in some place. So we are storing that thing in the some spatial register. So this array means is return address register. So return address register. Okay. So among the 32 registers in the MIPS, there is a spatial register of which name is return address. So that register is changing when jump and link instruction is called. So when jump and link instruction is called, then array register is containing the caller's location. Okay. So actually this is third ones. 31 register. Okay. Okay. So using the jump and link like some function. So we are specifying the label. Okay, so this is just label. Then jump and link is jumping to some location, the label. Okay, so here there is some instructions. And then finally, what we have to do is that we have to go back, right? Go back to the next address of the jump and link, like add. Okay. So the return address is actually stored in the array register, right? So we need some instruction, which is just looking at the content of register. So we need some another instruction, which is jump register. Okay, so jump register format is just simple, jump register, and some register name. Okay, so that's the format of jump register. Jump and link case, jump and link, we need label, which is constant. Okay. So here, normally the $F case, jump register and $RA. So then array is containing the address of add. Okay, so that is how this is gonna be working. Okay, so then let's look at the simulator, how this is really working. But before we are using the simulator, what you have to know is that the MIPS is a little bit awkward for this branch and jump. So instead of jump instruction or jump and link instruction case, array is not containing the pitch plus 4. Instead of that, it is containing the pitch plus 8. Okay, so that's the only difference. So what you have to do is that jump after you're calling the jump and link, you have to add no operation. Okay, so after is jumping to some place, then this should be coming back to the next instruction. Okay, so that is how this is gonna be working. Okay, so then let's look at the original case. Before that, let's look at some code. Okay, so let's get the simulator. Okay, so so you can see the simulator, right? Okay, so here let's try to write some code. First, we are calling the function f. So in order to call the function f, we are writing down the jump link instruction. Jump link f function and add no operation. And then here we are just code. And code. Then let's try to write down the code here. Let's do anything. And then let's do the jump register array. And After jump instruction, add no operation. Okay. Okay, so can you run the code? So when you're starting the code, jump and link instruction is starting. So let's look at what the rest value in array. So array is currently 0, right? Array is, so here there are two names, R13, 31, and array. Array is another nickname of the register. Okay, so array register value is 0. When you are running the code, then the return address is changed to 40008. Okay, so when jump and link instruction is executed, the current PC value was 40000, right? It was 40000. So array is PC plus 8 value. Okay, so that is storing the array register. PC value is array value is storing that value, and then no operation, and then it is jumping to this location. Okay, because jump and link is jumping to that location. Okay, so PC value is 40010. So we are calling these functions step, and jump register. Jump register instruction is jumping to the 40008, which is line 3 add instruction. Okay, so we are skip. No P is executed, and then jumping to the add. Okay. And then step sub. And if we are stepping, then it is just going to the next instruction. So actually, this is incorrect code. Okay, so it is infinitely looping because this is incorrect code. Okay, so anyway, to implement the function call, we need two instructions: jump and link instruction and jump register instruction. To call the function, we need to use jump and link. Return back from the call leaf function, we have to use the jump register instruction. Okay. Okay, so can you run your simulator, whether this is really working? So can you try in your simulator that code, and really it is happening. So if you can see the same result, please let me know through the chatting. So just put the OK in the chat window if you can see the same result. Okay, so I think everyone is completing. Okay, so in the simulator, we know that there is some nickname of the register. Okay, so we'll learn about this nickname actually. When we are looking at the function code, we have to store the argument, right? So we have to store the argument, and also we have to store the return value. So where we have to store that argument and return the value. The faced memory space in the processor is a register. Okay, so if it's possible, it's much better to store the argument and result in the register. So the registers are actually used for that function argument. So register A0 to the A3. Register A0, A1, A2, A3. That is for the argument, function argument. Okay, so so there are four registers for the function argument, which is actually register 4 to the register 7. Okay, and then for the return the value result, in C code we are only supporting the one return the value, but actually in the MIPS it can support two register value, $V0, $V1 result value. Actually that is register number 2 and then number 3. Okay, so that's the nickname. And you know that the last thing, return address, which is register return address. Which is register number 31. Okay. Okay, so then let's look at the code and let's generate the MIPS code using these registers. Okay. So anyway, you know that $A0 to $A3 are supporting the argument, and $V0, $V1 is containing the result. Okay. So then let's look at the original code, which is integer main and is calling function f2, 3, and function is 2 argument and return a plus b. So let's look at how to generate the MIPS code for this function. Okay. When you're translating, the name of function is translated the label. Okay, so label of main. Traditionally, in C compiler case, it is adding the underline. Okay, so to generate the label name. So that's the convention. Okay, so what we have to do is that we have to give constant value 2 and 3 as argument, right? So 2, which register do we have to store of the constant 2? It should be stored in the A0, okay? And this should be stored in the A1, okay? So to store the 2 and 3, we have to call add I instruction. A0, 0, 2. A1, 0, 3. Okay. Then we have to call function f, right? So to call the function f, what instruction do you have to call? Jump and link instruction. Okay, F. And then the operation. And then we are done, right? Done. Okay. That's all. Actually, here we also have to return because this main function is actually called by the operating system. Okay, but we are not considering the operating system. Anyway, we have to implement function f. Function f case, function when we are compiling the function f, we know that the first argument is stored in the A0 register, and second one is stored in the A1 register. So we have to do add. We have to call add instruction A0, A1. So where is the destination register, do you think? Yeah, result should be stored in the V0. Okay. So we are completing. So $V0 is containing the result. Okay. So result is containing, then we are something that jump register array. Okay. So this is completing of the code. So can you write the code in the simulator? Okay. So somebody is asking me that the array register is containing 4004 plus 4. So she is asking like this. For instance, this is address jump and link is starting 4000. Okay. So then where is the returned address? Okay. So where is the jump and link array register value? So when this is called, then array is 4000 plus 8 always. So A means that it's next instruction. Okay. So maybe you are learning this code, then the jump register instruction is actually jumping to the add instruction, right? So everyone is working. So if you can, then please let me know. So you just put the OK in the chat window. If you have any problem, please let me know. So I want to see your code if your code is not working correctly. So can you say your result in the chat window if it's working? Okay, so it's okay, right? So you can follow how to translate function code in the MIPS code, right? Okay, so then let's go to the little deeper things. So we will learn about the memory layout. So memory. This is memory. Let's say the first one is 0 and last one, the bottom one is maximum address. Okay. Then, so some part, this is just reserved, okay? It's not used anyway. Some part, this part is called text region. So actually text region means it is including the code. Okay, so machine code are actually stored in that memory location. So when you are compiling and then when you're starting the application, then the first part, okay, first part is storing the code, so machine code, and then next part is data. So data is actually including the static data. So static and global. Static, global data. So when you are writing the C code, in the C code, you're writing the function, and inside the function, you're in the static variable, right? And outside, there is some global variable. So this global variable and static variables are located in the data region. Okay, so every global variable which is declared outside of function and any static variable are allocated in the data region. Okay, so that's a fixed one. And then in C code, sometimes you're calling malloc, right? X equal malloc. So this is dynamically memory allocation function. So malloc things is stored in this location. So that is called heap. Okay. So heap is growing. Whenever you are calling the malloc, then heap is growing, so is allocating, and then you are calling free. Then, so this malloc is allocating some heap, and another one, and another one. And then maybe if we are calling the free, then some parts are just freed. Okay. So heap library is managing that memory allocation and free things. But anyway, heap is generally increasing the from the lower address to the higher address. Okay, so heap is growing this location. And there are last variable, which is just local variable. This is local variable. So when you are declaring the variable inside of function, that variable is only used inside the function, right? So whenever the function is called, then the local variable is created, right? So to store that local variable, we are using stack region. Okay, so maybe you learn about the stack data structure, right? Do you learn about that? Stack. Do you have any problem for my writing? Okay. So here, heap and stack are region. Heap region and stack region. Actually, you learn about this heap and stack when you're learning about the data structure, but this term of heap and stack are a little bit different from the data structure. Okay, so heap and stack is similar to the data structure terminology, but it's not. Okay, so data structure case, heap is just like a tree structure, right? That's the heap. But in this case, it's not the tree structure. It doesn't need to be, okay? It's not. Stack is like this. Data is coming in, and then when it's returned, then the first in is go out, right? So last in and first out. That is stack. But anyway, stack is going from the higher address to the lower address. Okay, so whenever a function is called, then new stack area is allocated for that function. So stack case. So this much for the main function. And then main function is calling f function, then this much is called the function f. Okay, so main function is there, and this is calling f, then the location for f is allocated. F function is calling another f, like a recursive call, then another f is allocated. Another f is allocated. Okay. So if this is infinite time called, so if we are writing the recursive call without caring, then it can be infinite time recursive call, right? So that means stack is growing, then it is reaching to the heap location. Heap region and stack regions are crossed. In that case, it's generating the memory error. Memory, maybe you are seeing that memory segmentation port. Or sometimes you see that memory page port. The reason is stack is growing whenever it's called, then it's reaching to some another memory region, then it's generating this kind of fault message. Okay. So heap case, it is managed by the malloc. So the malloc library is handling. Stack case, when you are generating the code, we have to manage this stack area. So to specify the top of stack, so top point of the stack, there is a special register which is called stack pointer. Okay, so there is a stack pointer register, which is pointing the top of the stack. Okay, so whenever a function is called, the stack pointer is changing. Whereas function is returned, the stack point is also changing. So here we know this address registers. There is another one, stack pointer. Which is register 29. Okay. Then who is managing the stack pointer? So array register case, jump and link instruction is changing, right? Stack pointer case, you have to do. So compiler has to do. So explicitly, we have to change in the stack pointer value using the instruction. Okay. So there is no automatic mechanism to change the stack pointer. Okay. So then let's look at some code. Let's look at a little complicated code. Okay. So let's look at this code. Integer f int a b c t. So there are 4 arguments. And then here we are declaring the local variable E, which is 100 size. Okay, and here K is 4 word size, and then return A plus B plus C plus D. So let's think about what is happening. Okay, so the G function G is actually calling F. Okay, so if G is calling the function F, then what's happening? So let's look at it. When function G is running, so let's look at stack. Okay, so let's only look at the stack region. So G is using this much memory area. Okay, so at this moment, stack pointer is pointing the top of the memory. Okay, then function F is called. We have to prepare that some memory location for this function F, right? So how much we have to prepare it in this case? How much? How many bytes do you have to prepare in for this function F? So how many local variables are there in function F? 104 word, right? So it should be 104 word is 104 by 4 times byte. Okay. So how much is it? 416 byte. Okay. So then what do we have to do? What's the SP value? What's the new SP value? What do we have to do? Do we add of 416 or do we have to subtract? Yeah, we have to subtract because stack pointer is decreasing when we are preparing the new memory location. So function F is called, then we have to reduce the stack pointer. So when we are generating the code for this function F, what do we do? First, we have to decreasing stack pointer by 216. Okay. So constant subtraction is actually we have to use add I with negative value, right? So we are decreasing the stack pointer value. So this is a stack manipulation. And then we are running the main code. So we are A0, A0, A1, A0, A0, A2, A0, A0, A3. Okay. So we are generating the code. So we are completing the addition of these 4 variables. What is next part? So we have to return, right? We have return. So before we are returning, what we have to do? Before we are starting the function F, we are increasing the stack memory area, right? So we are allocated some stack region for function F. Before we are returning from the function F, we have to delete it. So we have to remove the memory area for function f. So here, we have to stack pointer changing. What do we do? Last part. Okay. So stack pointer was decreasing. Now it is increasing, right? So stack pointer is going back to the original value. So this is another stack part. Stack manipulation. And then we are jumping. Okay. So always when you are generating the code for the function, you have to generate the stack manipulation first, and then generating the main code, and then you have to we have to add another stack manipulation code and then return back. Okay, so for part should be you have to write down. Okay, so then let's look at this example. Int f, int a, int b, and inside to that there is local variable c, of which size 2, and c0 is a, c1 is a plus b. Return C1. So can you generate the code? This code. If you are completing, please upload your code in the chat window. I will give you 5 minutes for this problem. Okay, so then let's get how we are generating the code. First, we have to generate in the label. And then we have to generate in the stack manipulation. Okay, add I, SP, SP. And how much do we have to prepare? Yeah, -8. Okay. And then we are generating the code. So it is storing the A's value into the local variable. So we have to store. The location is stack pointer location, right? So we are just simply thinking that this part was something, and this part is F. So first part is C0, and second part is C1. Okay, so this is SP. So first part, A0 part, we are storing the A, which is A0. Okay, argument A0 variable is stored into the C0 location. And for the next one, we have to add A plus B. So add A0, A1, and which register do you want to use? Any is okay, but let me just use the V0 because we know that V1 is returned. Okay, so then what do we do? Store, right? Store V0 value into where? SP and C1, right? Okay, so the following one. So we are completing and then we have to return. Before we are returning, what we have to do? Stack manipulation also. So add I, SP, SP, and original one, 8. After that, we are jumping back. Okay, so this is the code. So any function is given, you can translate, right? Okay, so then let's look at some function implementation, which is calling another function. So function is calling another function, like a recursive call. So let's look at this example. What this function is doing. So there is a fact, argument is n is less than 1, is returning not f, returning 1. Okay, so returning 1. Otherwise, is returning n multiply fact n minus 1. So this code is computing n factorial, right? So n equals 3, then 3 times 2 times 1. So that is this function is 2. So let's generate the code for this function. Okay. So how we are generating the code. If let's say n is less equal to 0, okay, so simply we are saying that it's n times minus 1. Okay, so we are trying to generate the function. Okay, so first it is fact variable. What do we do first? Stack manipulation, right? So always you have to stack manipulation. Add I, SP, SP, and something. So currently we don't know how much we have to allocate for the stack. So just leave it as a blank. And then what do we have to do? So this function case, inside this function is calling another function, right? For this function, what instruction we have to generate? For this function call, we have to execute jump and link instruction, right? To call the function, we have to always generating the jump and link, right? Jump and link instruction is destroying the array register value, right? When jump and link instruction is called, executed, then array register value is changing. Am I right? There is some another function which was calling this function like this. Main function was calling fact, right? So this function is called, then this is jump and link, and jump and link is calling jumping to here, this location, and also return address is set, right? But that return address will be destroyed another function call. So what do we have to do? We have to store this return address. So before we are calling this return address, I mean jump and link, we have stored the current return address. Okay, so whenever a function is containing function call, then we need to store return address in some memory location. So which is available memory location in the function? Stack is the available memory. Okay, so whenever new thing is generated, then we have to store in the stack. So what we have to do is we are storing return address. Okay, where the first location on stack. Okay, so at least we have to store array register value in the stack. Okay, maybe we need another one, but currently we don't know that. Okay, so then what's the next instruction? So after completing the stack manipulation, we have to check n is 0, right? So which function do we have to call? Branch equal or not equal, right? Branch equal, not equal. N, which register do we have to look at? A0 register, argument 0. And 0 is 0. If it's true, then this is if true case, right? If it's true case. This is true case, we have to do return 1, right? Return 1, that means V0 value should be 1. So we are setting V0 as 1. Otherwise, what do we have to do? Otherwise, we have to do this part, right? So we have to call another fact. So before we are calling the fact, what do we have to do? We have to decreasing n, right? We have to decreasing n. So we have to rephrase here. Okay. we have to decreasing A0 value. And then we are calling the fact function. Jump and link fact. Okay. So after jump and link, then what will be returned? Which register is contained return value? V0 register is contained return value, right? That's our expectation. So V0 register is contained the return value. So using this return value, what do we have to do? We have to do multiplication, right? So maybe we have to multiplication V0. Where is n? Do we have n or not? Originally, n is in the A0 register, right? A0 register is containing the n value, but A0 is already destroyed, right? Because we are calling some other function, fact. So then what do we have to do? N also should be preserved. N should be also stored in the stack. So we have to store A0 value also. Okay, so storing the return address, but also we have to do n value, right? So we are storing the n. Okay. Then before we are calling the multiplication, we have to restore. Restore. Load word A0 for SP. And then here A0 V0 is contained return value. Okay. And then we have to return. So here we have to skip this if part, right? This else part, we are jump. So there is exit. So here we have to manipulating the stack. So before we are reducing the stack pointer, we have to restore the array register value. SP, and then SP is restored. And jumping back. So how many words do we have to store in the stack? 2 words. So we have to specify 2 words. Okay. So when you are creating the code, sometimes when you need store some register value in the memory. In the case, that should be stored in the stack. So that much should be prepared and then restored in the code. Okay. So next time we will write this code and we will look at how this code is working. Okay. So we will continue about this project goal and we will look at some other things. The midterm exam will be April 28th. Okay. So will be 28th. It's Wednesday, I think. So I already announced in the portal site. Okay, so and the midterm exam will be covering the chapter 1 and chapter 2. So mainly is chapter 2, which is translating the MITS code from the C code. And you can also use the simulator. So in the simulator, you can check whether your code is correct or not. Okay. Any question? Okay, then see you on Wednesday. Bye.